Yeah, thank you, Babette, and thank you, Eka and Michael and Raymond for this invitation. So today I'm going to be talking about rheology of sheared sediment beds, so heavy particles that make up the dense suspensions, such as the mudslides we've seen today before in Jeff's talk. And I'm going to be tackling this problem in terms of particle reserve simulations. So just to give you a flavor of what a mudslide or debris flow could look like, the classical example is usually taken from the Ölgraben in Switzerland. So this is a map of Switzerland, and there's the town of Sion. Sion, you can see it here in the valley. And the Ölgraben has some very steep slopes with highly erodible rock material. So there's always loose material on the mountain slopes. And with heavy rainfalls, you get mudslides that look a lot like this, or you have a dense suspension that changes the viscosity properties of the sediment, but you also see that it has the potential to move very large boulders downslope with, of course, very destructive potential. And we expect these events to become more and more frequent in the future due to climate change, as that changes rainfall intensities and other things. So here, this catchment is very well controlled because people are aware of it, but of course there are different situations like the Montecito mudslides where you have stronger impacts. Another example is shown here. That's also after a heavy rainfall event in New Zealand. It's called the River of Rocks, and so clearly this does not behave like a regular river would behave in response to rainfall events. And so then this is where we start thinking about rheology. And the way we access rheology is that we plot the shear rate against the shear stress that is exerted on the fluid. And if that ends up to be linear, then we call that Newtonian, and that's the clear water case. And with the suspensions, we're more or less on this branch here, where we have a dilatant or shear thickening behavior that is caused by these particles in suspension. So, and then we decided to focus on the non-cohesive part, where we look at rather large grains. So think of it as sand grains in suspension, and we don't have any electrostatic interaction, nor do we have any cohesion acting on the particles. So yeah, so now the question we're asking is, how do these suspensions flow, and can we describe these in terms of rheology? So in order to do that, we take constitutive equations that have been derived from classical rheometer studies. There are two prototype situations where you have neutrally buoyant particles in a fluid, and then the volume imposed setup says that there are two walls that are always at the same distance, and then you shear the suspension to see what the stress exerted on the particle is in terms of in response to a shear rate. Another way to think of it is that you have the upper wall movable not only in this streamwise direction, but this is also movable in the vertical direction, because as you increase the shear rate, you would see that particles are dilating as they slide past one another. So volume fraction becomes a function of the shear rate. And so if particles want to expand, then they can do that by moving this upper plate vertically. And the way we work against that is by a pressure that we impose from above, which we call the particle pressure. This scenario is very interesting in terms of sediment transport, because it bears analogy to sediment transport when you think of sediments that are acted upon by gravity. So you have a submerged weight of the sediment that pushes on the underlying sediments. So the deeper you go into your sediment bed, the higher your particle pressure becomes. And that's what we want to exploit. And those two frameworks can be recasted into constitutive equations. If you think of volume imposed, classically, you would think of the shear stress and the granular pressure as a effective viscosity that alters the clear fluid viscosity, eta F, by some prefactor in the shearing direction, but also in the normal direction as a response to your particle pressure. Another way to think of it is the macroscopic friction rheology, the mu of J, where you have the macroscopic friction as a function of the non-dimensional shear rate J, and also the volume fraction, since we are able to expand our sediment bed, becomes a function of that too. And those can be used, and we can actually directly measure with our approach all these quantities in red to get constitutive equations for those that we can then use for rheology models in sediment transport modeling. The way we do that is by solving the complete Navier-Stokes equations. So we always have the fluid in all of our domains. And then we use the immersed boundary method. And so maybe to distinguish myself from Jeff a bit from the talk this morning, what we do is we have particles that are larger than the grid cell size of our fluid solver. And so we are actually resolving the fluid around the particles, and we get the hydrodynamic forces as a direct result. And that incorporates everything that has been shown to be modeled on the Monday's talks in terms of the Maxey-Riley equations. We don't need to do any of that because everything is directly computed by geometrically resolving the particles. And then, of course, we have buoyancy and we have collision and contact. I would also like to emphasize that we are resolving lubrication forces, just like Jeff described it very nicely this morning, but we are not accounting for the electrostatic repulsion that he was showing, because those mostly apply for nanometer scale particles, but not so much for sand grains. And then for collision and contact, we developed some nice algorithm together with a grad student from Eckert's group, Edward Biegert, and we validated that against some benchmark cases. Here, for example, is a particle colliding with the wall. Here's the experimental data, and we follow that trajectory very nicely in terms of rebound, height, and speed. And then we moved on and applied this scenario to sediment beds. So these are roughly 4,300 particles in a channel. We let them settle, and then we create the sediment bed. And then we start shearing it with a pressure gradient in the streamwise direction. We apply periodic boundary conditions in streamwise and spanwise and walls at the top and the bottom. And we choose the parameters in according to Pascal Osselous experiments that has been conducted with Babette. And Pascal will tell you all about it this afternoon session. But this gives you an impression of what she did. This is a view index matched particles, and you shine a laser sheet through the sediment, and you could actually track the particle trajectories. You also get fluid velocity profiles, and then you can do two-phase flow modeling in terms of the Brinkmann equation, where you can also arrive at the momentum equation for the mixture that includes stresses by the particles and stresses on the fluids, and that's in equilibrium with your momentum supply in terms of the pressure gradient, how you drive the flow in the channel. And for those two stresses, for the fluid phase and the particle phase, you need effective viscosities and you need the macroscopic friction. So let's try to look into that with our numerical simulations. We do exactly the same. We drive a pressure gradient in our channel, and then we have all those particles. We can compute the fluid velocity profile in terms of a horizontally averaged profile. We have the particle positions. We vary the flow rate to get different flow conditions. And then we can reconstruct the entire mu of J rheology framework from that. And this is what it looks like compared to many other data sets. And I also would like to point out empirical correlations by François Boyer and also by Jeff Morris and Francois Boulet. And our simulation results are the dots. And so let's focus on the simulation results. And we see that those fall very nicely in between the envelope of those two empirical correlations. So we found pretty good agreement with previous works on rheometer studies in terms of our mu of J curve. Second, we have the phi of J curve, and there we also just focusing on the experimental simulation results, and we follow the same behavior with a slight offset towards higher volume fractions at a certain shear rate. Then we furthermore compare against the volume imposed framework in terms of effective viscosity. We again follow the empirical correlation by Jeff's group very nicely, and we found same trouble in the discrepancy at very low volume fractions here as well. And why that is probably because, or we think that if we took the effective viscosity in the shearing direction and separated the stress components from the fluid phase and the particle phase, we find very distinct difference to rheometer type setups. So we find that in the dilute regime, of course, everything is dominated by hydrodynamic stresses, and at a volume fraction of about 0.3, we are transitioning into a particle contact dominated stress, and that's where classical rheometry correlations hold. But in the dilute regime, we're more or less scaling with the Einstein relation all the way up to here. And if you compare that to simulations from rheometry situations, it behaves rather differently. And so that tells you that with sediment transport, you have the situation that you're rapidly transitioning to the almost jammed state to the dilute state, and that transition is your sediment transport layer. And so a lot of those hydrodynamic effects are screened in this porous medium transition, and so we think that's a key difference in our in our situation as compared to rheometer studies. Okay, so that concludes the first part of my talk, and the second part I want to talk about is a different simulation campaign that we ran to investigate polydispersity. So here, a slightly different setup. We have polydispersed sediment beds, and we shear it by moving the upper plate, and that's akin to reproduce duct experiments together with Morgan Hussain that has been mentioned many times already in this conference. And so we think that this bears analogy to sediment beds, and so we were interested in what's the role of polydispersity, and also as you move to very, very low shear rates inside the sediment bed, what happens there. Yeah, and this is basically recapping what Morgan's experiment looked like. So it was a rheometer with index matched particles inside, and then it had been sheared by the upper moving plate, and then it has been monitored for a very long time to do a very long time averaging of it, and it's also a pressure imposed setup with a movable upper plate. So then we focus on polydispersity by varying the ratio of the largest to the smallest grain, and we denote it by monodisperse, and then we have poly 10, poly 50, poly 100. So the higher that number is in the poly label, the higher our polydispersity. And we see that those are the grain sizes that we get. And then first, let's check with Morgan's experiments, but also with the data by François Boyer. This is the empirical correlation put forward by François Boyer. All the way spanning from 10 to j equals 10 to the negative 5 to some very large value of j. And we see that our data follows this data very nicely. So François' data is in green. Our data is the hollow circles. Oops. And Morgan's data is here shown in red. And so we are basically reproducing the Boyer rheology at higher shear rates, but there's a bit of a deviation here that I will get to later. But this is very encouraging already, and we found the same deviation that Morgan did with our rheometry simulation. And second of all, we have the phi of j, and there again we follow the curves very nicely. And here's François' data, Morgan's data, and we are doing the same. And we have this empirical correlation put forward by François Boyer. So now what we do is we brute force calibrate or fit those empirical correlations to our polydispersed system to obtain the functionality of Kn, phi m, and also mu2, mu1, and jf on the polydispersity, right? So because we want to see if there's an impact. So first of all, what we see is in the phi of j curve, that phi m increases as you increase polydispersity, and that has been discussed at this meeting many times already, and it's kind of obvious if you think of small particles filling in the gaps in between large particles, and so that's pretty good. And so what we also found is that Kn systematically decreases as you ramp up polydispersity, and you find the same for mu1, which is dictating this leveling off here, and mu2, which is the leveling at this dipping here. And we also see that mu1 and mu2 systematically decrease, and we didn't find such a good correlation for JF, so we just take that as a constant, but we can express all those empirical functions here, or empirical coefficients, as a function of phi m, and those are the colored lines here, and those yield very good agreement. So now let's but that's only for the large shear rates, so let's take a bit care of the low shear rates here. And what, if you look at the Boyer model, and that comprises frictional contacts, it comprises hydrodynamic contacts, and the hydrodynamic contacts take care of this part of the curve. The frictional contact basically describes this dip here, But what's missing is another dip here. So we just propose to use another term that has the exact same shape and format of the frictional contact term that allows us to fit and calibrate our model to the data of Morgan, but also to ours. And if we use that, we find that and we call that the creeping regime because we're looking at very low shear rates. If we use that, then we can use this model in green here or derive it and fit it so that we get very good agreement with all this data. So that's the extension that we've put forward, and I'm happy to discuss that with all you guys. And then maybe as another heads up, we're currently running simulations on rheometer studies, aiming to reproduce Franco's work. Franco will be right after me. He's sitting right there waving. And Sudarshan, who's my postdoc, is currently running those simulations. And so we're happy to talk to you about that also. The focus of this work will be to investigate the transition from the viscous to the inertial regime as we go to higher and higher Stokes numbers in terms of particle inertia. All right, so with that, I'm already at the end of my talk and I'd like to conclude. We investigated the shear thickening behavior of sediment beds, where we discovered that there is a dense regime that is contact dominated, and we can use the classical empirical correlations for mu of J. And there's a dilute regime where the hydrodynamic stresses dominate, and we should rather use the Einstein relation for this regime. And that is because those hydrodynamic effects are screened by the porous medium and the rapid transition of the sediment transport layer. And then we looked into the effects of creep and polydispersity, where we find that we can express the mu of J as a function of phi m that varies with polydispersity, and that can actually become a measure of polydispersity for that matter. And then we looked at the creeping deformation and found that the macroscopic friction coefficient decreases to about 1/3 of the original mu of J values for the creeping regime as another indication of the flowability of the system. And that is regardless of, or that's basically independent of the polydispersity. At least that's what we found. So all the polydispersed simulations reproduce the same behavior in the creeping regime. Yes, and with that, I'm at the end of my talk, and I would like to acknowledge all of my collaborators, and yeah, thank you for your attention.
Thank you, Bernhard, for this great talk and beautiful simulation. I'm sure there are many questions, so we start here. And then,
hello, very nice simulation. I just one question about slide 16 because I didn't understand. It was very rapid. Just a quick comment. The Reynolds number of the fluid is typically which value?
Oh, okay. This is all laminar, right? So
yeah,
this,
so it's 1 or 110 or...
Yeah, something like that. Yeah.
Purely viscous, okay.
Right, highly viscous.
In fact, I haven't understood the difference between the two red curves when the particle volume fraction is around 0.2. You said it, but I didn't grab the difference between the two curves, the red one.
So this...
When the solid fraction is around 0.2, yeah, 0.1 or 0.2, the phi value, you told it, but what's the difference between the two curves?
So this is our data, just the particle stress.
Okay.
This is data gathered from the study by Sagnier-Gaillet, which is numerical simulations of rheometer type simulations.
Yeah.
And this is the hydrodynamic part, and again, what?
Sorry, what's the difference between both?
So ours is the sediment transport, where you have stuff laying on the ground, and this rapid transition in the sediment transport layer.
Okay.
Rheometer studies classically are carried out using neutrally buoyant particles with homogeneous suspension. Right? Okay. So we have this inhomogeneity at this sediment transport layer that we need to account for.
Okay, so I was wondering. And so your, just to finish, your simulation seemed to be more dynamic than the exponents of Pascal. I mean, the velocity profile, I didn't see the exponential decrease.
Right.
Am I wrong? Or?
So we ran it for 3 flow rates, and So the one that I showed was the orange and the blue line, and they were not close to the jamming, so the entire bed was in motion. The one in green was like that, like as you described. So, okay. And also the polydispersed simulations were very much like you were describing it, with the exponential decay into the sediment bed.
Thank you. Very nice simulation. Yeah. Anyway.
Thank you for an illuminating presentation. One of the Achilles heels of the mu of rheology is that it doesn't say anything about boundary conditions. So could your simulations be exploited to inform that problem in a practical problem in engineering? We need boundary conditions to know what's going on from the boundaries to the inside of the flow. The inside of the flow is the consequence of what the boundary conditions are.
So when you say boundary conditions, you mean the bottom roughness or something like that?
Well, you know, it's as if you had the viscosity and the density of your fluid, but you had no idea what the boundary was doing to the fluid. You know, no slip conditions does not exist in a
yes,
in the granular mechanics kind of system.
Yes, that I agree with. So we explored two types, which is the way we drive the flow, so pressure imposed versus, or pressure driven, Poiseuille flow versus co-ed flow, and that didn't really affect much the rheology. And also we looked at the polydispersity, which is also like a boundary conditions, also in terms of bed roughness. I don't know if that answers your questions, but no. Okay, then maybe we talk later and discuss what kind of boundaries we could define. Of course, yeah. Thank you.
Bernhard, thank you for the nice talk. So I have a question. So, I mean, it seems that this field is getting really along and really quite far. And so what are in your opinion, what is one of the questions that you would like to solve within the next 5 years? Yeah,
this is the hearing, right?
Is the boundary condition. What is the thing that you think is really in your opinion, if you want to tell us? I mean, I don't know.
I mean, there is two obvious things that we're currently working on. One I mentioned already. One is the transition from going from the viscous to the inertial regime, and Franco will tell you more about that, but we're currently running a campaign along those lines. And another one would be the question, what happens if you make those particles cohesive with extreme polydispersity, perhaps, so clay sand mixtures, something like that.
So do you get approached by the concrete industry to tell them when the concrete is going to be good and when it's going to be bad, like mixing?
Yeah, that's rheology. Because
mixing clearly is a very important question.
Yes.
Kimber.
Thanks. Really great talk. I like this work a lot. My question is about the polydispersity. And I think that it's in some ways I want to know what your, like, if you've thought about a definition or two things to put together that is representative of polydispersity. And here's why I ask, because we did some simulations, and I can send you the paper, with dry particles, but only bimodal, and just different concentrations of each of the two species. And we saw the sort of the same change in the maximum packing fraction, if you will, for a 50-50 mixture compared with a 25-75 mixture compared to a 1-0 or 0-1 mixture. And but the it's just they didn't have a difference between the, I'm sorry. The main thing is, okay, so the difference between the biggest and smallest is part of it, I think, but also there's like the quantities of the different parts in it. And I think that would also be helpful for engineering problems as well as geophysical problems to sort of use. And I guess, in Michel's wording, it would be very useful, and maybe your simulations could be exploited for that.
Right. So we ran a simulation like that. So this is the initial condition, look from above, and that's the end. What we were interested in was the question of grain size segregation. They produced exactly the same phi m for our simulations, and it was the same rheology. So to answer your question shortly.
It doesn't really answer my question, because I guess you saw with different definitions, according to what you said, of polydispersity, which is like this 100 or 80 or 20 or whatever it is, that's representative of maximum minus minimum. It's it shows different results, different curves. And so I'm wondering if you see similar differences between poly 100 and bidispersed 100, for example. And so maybe, you know, that I'll just put that out there as different types of polydispersity. Do you see the same things on the plot?
I think that it's the value of phi m depends differently on for polydispersed and bidispersed systems. So it will be two different curves that you would be creating. You see here, this is a ratio of 2, and this is a ratio of 10, and yet this is what you need to get the same phi m. So
I think that it's sort of still an unresolved case unless there's more than these two examples.
Of course, yeah.
My question's related to Michel. So, you know, you have the particle pressure in these definitions, and that's 0 on the surface of the particle. So you have trouble with these definitions of J and I, and that relates. I wonder if you've considered when the flows get shallow, and then the granular flow would normally have a linear velocity profile. So it would actually disagree with these type of models.
Mm-hmm.
Be a very interesting case to study.
Yeah, I think, you know, that empirical correlation has been designed for dense suspensions in the first place. So there may be a situation for very dilute systems where it may not be all that applicable.
No, I'm talking about completely dense systems. If you have a shallow flowing granular layer, you'll get a linear velocity profile.
Uh-huh.
And you know, you have trouble with things like mu by rheology because I is infinite on the surface, where the particle pressure goes to 0 and you can still have shear. So studying this, exactly what you've done, but with something that's, say, 10 particles thick, would be very interesting. So it looks like these models work very well in some situations, but it'd be really interesting to look at where they fail, at least for dense flows, and what's going on there.
Mm-hmm. Thank you. Yeah.
Oh, thank you, Bernhard. Very interesting and very nice. I had a comment about Kimberly's question and then a question. So regarding the polydispersity, we simulated with different polydispersity and bidispersity, and we found if you could just empirically even determine the maximum packing fraction, you could really understand a great deal of the rheology, and that is such a simplifying feature that it shocked me that it could do that. But anyway, so that's not just for the viscosity, but also for the second normal stress difference. We saw this, which is, you know. Okay, so the question had to do with, in the depth of your system, you're still describing all of the stresses as rate dependent, right? They all are. And I wonder how much of the stress might actually be not rate dependent, because you have a certain amount that's going through contact networks which are rate independent. Right. And I wonder if you could pull out whether there is, because everything should be linear in the shear rate, and I wonder if the stresses in fact are behaving linearly in the shear rate in the deep bed.
Yeah, that's a good question. Yeah, that will require more in-depth analysis. I agree. Yeah.
But you could separate out the Sorry, from your data you can separate out the contact forces and the hydrodynamic forces, right?
Yeah, I agree. The data is there, but I just haven't done and thought about it. No.
That's not quite the whole issue, because contact forces can be rate dependent, but they could have they could also be rate independent, right? The contact force could be proportional to the rate. So I think it's actually just averaging out the shear rate and determining the rate dependence might require data analysis as opposed to just sampling. That's what. So.
I just had one quick response that the point Jim brought up. You can rescue the mu of I or mu of J rheology at the surface, as Morgan did in the experiments with us, by just realizing that the particle on the surface has its own self-weight as a pressure. And you actually, just that alone does away with the infinity at the surface, regularizes, and the rheology goes all the way to the surface. So you just have to consider the pressure of the particle.
Reply? I mean, we didn't need that measure because as we resolved the particles, we cut the particles in thin slices, so that was enough to not run into such trouble. So I don't know. Thank you.
Thank you.